Yes, Dave. Our final speaker today, this workshop, is J Smyth, who will tell us about integer symmetric matrices with spectral radius less than 2.019.
Great, thank you very much. And the first thing I should say is that, as you see, this is joint work with James McKee in Royal Holloway. Now, so the polynomials I'm going to be considering are simply the characteristic polynomials of an integer symmetric matrix. So, of course, all the eigenvalues are real, and for example, the integer symmetric matrix could be the adjacency matrix of a graph. So the spectral radius is the absolute value of the largest eigenvalue, and I'm going to split my talk into two parts. The first part is where the spectral radius is at most 2, and the second part is when it's in this small range here. Now, if all the eigenvalues are smaller than or equal to 2, then if you replace x by z plus 1 over z for an integer symmetric matrix, then this polynomial is a cyclotomic polynomial, and so in this case we're going to call a cyclotomic matrix, and if it's a graph, it's going to be a cyclotomic graph. This first part has already been published in the Journal of Algebra, which I've just obscured there down the bottom.
And for you, a graph could have loops also.
No, it couldn't. It couldn't have loops. No, that's an integer symmetric matrix.
You don't call that a graph.
Yeah, not at the moment.
Because for some of us
I'll come back to that. Yes, it's also
it's an
interesting
case
where the
to me.
entries are all 0 and 1, but
Yeah.
the diagonal elements could be 1.
Indeed. Okay, so I'm going to for both cases, I'll simplify the problem. First of all, we can assume that the A's we're looking at are indecomposable. If they're decomposable, then the matrix can be split into blocks. So that's the first simplification. In the case of a graph, that simply means that the graph is connected. The second simplification is matrix equivalence. if all the eigenvalues are between -2 and 2, then we can replace A by -A, or we can multiply both the ith row and the ith column by -1, and we can also reorder the rows and columns, and still the matrix has eigenvalues in this range. Okay, and that's the second simplification. And the third simplification is for the third simplification, we need Cauchy's interlacing theorem that says that if you have a symmetric matrix n by n, and you remove the ith row and the ith column, then the eigenvalues of the new matrix interlace the eigenvalues of the old one, and so we can use that to simplify our description. We assume that we've got maximal cyclotomic matrices, so that these cyclotomic matrix can't be obtained from a bigger one by removing rows and columns. So these are the biggest ones. So if we do all that, then we can restrict our attention to equivalents / representatives of indecomposable maximal cyclotomic matrices. So these are the ones we're going to find. Yeah.
Particular equivalence relation underlying.
It's that A is equivalent to -A, or
Before the three.
yeah. Okay, so that's what we're going to be looking at now. Yes, so here's equivalence between these various properties for graphs and more general matrices, and I don't think we need to look at that example really. Okay, now in the case that we've got graphs, the results are well known. So apparently this is due to J Smyth in 1970, that all the maximal cyclotomic connected graphs are these famous ones. So,
Do you know whether the same result existed before you for graphs with possible loops?
I don't think it did, but
It certainly contained
possible.
your results.
yes, it is. Yeah, yeah. Okay, so this is the result we're aiming to generalize. Right, so the first step is to look for matrices containing a big entry, and in this case it's easy. There are only two examples, the 1 by 1 and 2 by 2. Right, so thereafter we can consider matrices only with 0, 1 and -1. Now, first of all, we'll look at the case of signed graphs where the diagonal is 0. All the entries on the diagonal are 0, and so the way we'll draw them is this is an ordinary edge, and this is a signed edge. Okay. So, what graphs do we get? We get two sporadic examples and a family. And the sporadic examples look like this. Here's the 14 vertex 1, like so. Now, I claim that it's obvious that it's a cyclotomic matrix. Don't laugh, it really is obvious, because you can see every vertex has degree 4. Therefore, if you square it, you get it 4s on the diagonal, and if you choose any two vertices and say vertex I and vertex j, and look at the paths joining them, then there are either 0 paths or 2 paths, and these 2 paths have opposite sign. And so the square is 4. It's 4 times I, and all the eigenvalues are 2 or
So does that have
minus 2.
anything to do with the finite plane?
I don't know. It could do, but I don't know. It's can't get this to stay.
It's like the Hayward graph with extra stuff.
And then the 16 vertex graph is just a hypercube, and again it's obviously cyclotomic. If you square it, then you get 4, and then the family that we get look like this. They're tessellations of a torus, so that A and A should be identified, and B should be identified. And so here's a picture of it. Say in the case k equals 6, it's spiraled around like that. Right, so these are the, so we've got the 2 sporadic graphs and this family for k at least 3. And now we come to the case of possibly having ones and minus ones on the diagonal. Well, we've been calling these things charged sign graphs. That the diagonal elements are charges on the vertices. So, and in this case, you get 3 sporadic examples and 2 infinite families. And so I'll show you these guys. So here are the 3 sporadic examples. If you can see them. So these charges mean, as I said, that there's a 1 on the diagonal there, or a minus 1 there, and the spots are just zeros. So there are those 3 examples. I mean, those 3 sporadic cases, and then there are. I don't know if I've got room for them. There are these 2 as well. Now, these aren't tessellations of the torus. They're tessellations of a sausage, and at the end are charged vertices. Right.
In your list, I don't see any that are charged graphs without signs. Is that because they're equivalent to something else?
No, you can find them by deleting vertices.
Oh,
And
I mean they're
yes,
maximal within the class of graphs.
the maximal ones are all yes. But if you want only ones on the diagonal, then you can chop them out.
No, I'm worried about the minus ones off diagonal. You can't get rid of those.
So you want everything
On
plus. You want everything
plus, but
positive.
But I allow charges on the vertices.
I don't think we get any of those.
I mean, shouldn't, for example, if you just take a path,
Well, you can.
with a charge at both ends?
Delete everything in the second row. of
Yes, here. Here, yes.
That's it.
Yes, there. Yeah, yeah,
Ah.
yeah, 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 yeah. 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 Okay. So that's the result. Those are the results for all eigenvalues at most 2. Now we come to the results for increasing the characteristic, the radius. So for graphs, the results are as follows: that it's known the spectrum of values of the spectral radius is achieved by either graphs like that, which are just a tree. I can just a tree with A vertices, B vertices, and C vertices, or something like that, and then beyond 2.058, there's a result of Shiro, which tells you that the spectrum is dense. But for general graphs, we can't get quite as far as that. So so here's we can only get up to 2.019, and so here's this tree, and then there are these sine graphs and a couple more. Let me see how to do this economically. Yeah. So, excuse me. For the spectral radius between 2 and 2.019, there are only graphs of this form and these examples here. The reason we don't go much further is that the tree T1 to N, the radius of that goes to 2.0198 as n goes to infinity. So that's a limit point, and so we weren't able to go to go as far as that. Right. So now I'm actually a number theorist, and so you might wonder why I've been delving in these things. So perhaps I should explain very briefly. So the kind of numbers I'm interested in, algebraic numbers, are Salem numbers, and they're almost roots of unity, except that they've got one conjugate bigger than one and one smaller than one, and all the others are on the unit circle. And these can be constructed using graphs, and I was hoping that they could all be, but I don't think that's going to be the case. So, for example, this graph, this 10 vertex graph gives us Salem number if you make the appropriate substitution in the characteristic polynomial. And then you can do the same for integer symmetric matrices in general. But I mean, this is the smallest known Salem number, and it's an unsolved problem as to whether there are Salem numbers. I mean, when I say smallest known, I mean that this number 1.176 is the smallest known Salem number, and it comes from this graph here. But it's an unsolved problem as to whether there are any smaller ones. Okay, I'll stop there, and thank you for your attention. Yes?
How is this Salem polynomial related to the cyclotomic? Is it a factor? Is it?
Well, it's only related in that if you remove a vertex, then you get a cyclotomic one again. you get a cycle.
No, I mean the cyclotomic one.
Yeah.
Like in field theory, you know the.
Oh yes, they're not related at all. No, no. Okay. And since I'm the final speaker, I'd like to thank the organizers for a great conference. Great, thank you.
We reconvene for the problem session when? 3:30?
Yeah, problem session at 3:30.
What's the format?
It hasn't been decided.